Hey guys, let's talk about these orbitals now in the molecules. So now we talked about valence bond theory, MO theory. Let's just look at this. O2 has this Lewis structure in this orbital diagram. What we're going to do here for O2, we have an internuclear axis that goes through the oxygen and oxygen. We're going to call that X. They have Z vertical. That means Y is coming in and out of the screen isometrically. So there's Y. Hopefully that makes some sense. And the actual XYZ coordinates, something like that. Something like that. Except X is kind of rotated, and that's in this sentence. So we're going to just delete that. So the sigma bond is right here on the internuclear axis, and there's the sigma. So that's the sigma. That's where the orbitals are overlapping, and you can see you get orbital overlap there. The pi bonds are around the sigma bond. So the pi bonds are around the sigma bond, and you got lone pairs in the py orbitals that are non-bonding. So these are non-bonding. They're not bonding. So you have a lone pair in this case a py. You have a sigma, and I don't know which one is the sigma, but let's just say one line. That's going to be a sigma bond. The other one will be a pi bond. And so there's the lone pair in the py. And then there's two pairs here that are not pictured, and that would be in the s orbital. Those are in the s, in the 2s orbital, in fact. They're just not pictured. So that would be the bond, the orbital, the electron density, probability of finding the electron for oxygen. Here's another one, formaldehyde. Here you have sp2 hybridized carbon. So you have sp2 hybridized carbon, hydrogen with its 1s, and oxygen that's not hybridized. So I like this one because it shows you the p orbital that's vertical here, this p orbital on carbon, right? In this case, it would be, let's call it the pz. The pz and the pz in oxygen are overlapping. And so we have, that's where the pi bond comes in. The sigma bond is still right on the internuclear axis between the molecule. I believe there's another picture here. So you can see this, I guess, green plane is a plane of the molecule. So every nucleus, the H nucleus, I guess the H nucleus would be over here. The H nucleus, the C nucleus, and the O nucleus are all in that plane. And there's the bondings. So the double bond is a pi and a sigma, of course. Then we have acetylene here. Acetylene is linear, so H, C, C, and H are all in the internuclear axis, which doesn't matter what it is here. And you have the 2p axis, the 2p orbitals that are unhybridized to make your pi bonds. So you got a sigma and two pi's. And last but not least, give you dichloro, so it'd be 1,2-dichloroethane and 1,2-dichloroethene. Right? The only difference in spelling is that A versus that E. And the E represents you have a double bond, and the A represents you only have a single bond. Kind of fun. The difference here is that the 1,2-dichloroethane here on the left can rotate. So the molecule can rotate. In 1,2-dichloroethene, we can't rotate. These chlorines are going to be on the same side of the double bond. You could have a 1,2-dichloroethene that has a Cl to a C to an H, double bond to C to an H to a Cl. You could do it that way, where they would be on opposite sides of the double bond. So in this case, the one that's pictured is on the same side. And the point is, double bonds cannot rotate. And that's something, if you're going to take another chemistry class, that's something that's important to note. So that's the orbitals and the molecules, what orbitals overlap with what. And we'll see you guys next time.